Hello, I'm Mingming Li. I'm a geodynamicist. I use computer simulations to study the structure, dynamics, and evolution of the deep interiors of the Earth and other planets. The title of my presentation is What Causes Seismic Heterogeneities Outside the LLSVPs in the Lowermost Mantle? This slide shows the global S-wave seismic tomography model by Rizima. Red color shows lower than average seismic velocities, and blue color shows higher than average seismic velocities. An important finding is that there are two large low shear velocity provinces, or LLSVPs, in the lowermost mantle, one beneath Central Pacific and the other beneath Africa. Outside the LLSVPs are regions represented by blue colors. These regions have higher than average seismic velocities, and they are often interpreted as ancient subducted slabs. This figure shows another global S-wave tomography model by French and Romanovich at 2,800 km depth. Again, red is low velocity and blue is high velocity. In this figure, the two LLSVPs are outlined by the solid black curves. An important finding is that, in addition to the two LLSVPs, lots of relatively small red blobs or low-velocity structures are formed in regions outside the LLSVPs. Here are other non-S-wave tomography models. We can see that all these models have widespread low-velocity anomalies outside the two LLSVPs, although the locations and the number of anomalies vary from model to model. In addition to these global tomography models, similar small-scale low-velocity anomalies have also been reported by studies using seismic waveform modeling. In addition to the low-velocity structures, seismologists have also found ultra-low-velocity zones, or ULVZS, above the common boundary. In this map, the pink color shows the locations of the two LLSVPs, and the red patches shows the distribution of ULVZs. The S-wave velocity reduction of the ULVZs can be as high as 30%. We find that many ULVZs are located outside the two LLSVPs. So, what causes the low-velocity structures outside the LLSVPs in the lowermost mantle? The first possibility is that they are caused by computational heterogeneities, such as the subducted oceanic crust. Here I show two examples of previous geodynamic modeling results. The figure on the top is by Christensen and Hoffman in 1994, in which the white color shows the subducted oceanic crust, and the figure at the bottom is a more recent study by our group, in which the green color shows the subducted oceanic crust. Our model has higher model resolution and a similar crust than before. The subducted oceanic crust sinks to the lowermost mantle in both models, and many of them segregate from the cold subducted slabs. Now, you are seeing the 3D geodynamic simulation results by Tackley 2011. In this model, a layer of subducted oceanic crust, which is shown here by the green color, is initially introduced to the top of the slab. After some time, the crust is separated from the slab and accumulates at the bottom of the mantle. The crustal materials have different physical properties than the surrounding mantle. They are also easier to be partially molten, and may cause low seismic velocity anomalies in the subduction regions of the lowermost mantle. We propose another possibility. The low-velocity structures are caused by hot thermal anomalies. Because regions outside the LLSVPs are likely relatively cold due to the influence of cold subducted slabs. An important question for this hypothesis is, how can hot thermal anomalies form in these relatively cold, subduction-influenced regions? Next, I will answer these questions through geodynamic modeling. The geodynamic modeling experiments are based on the solutions of several fundamental equations. including the conservation of mass, the conservation of momentum, and the conservation of energy. There is either no or extremely difficult to find analytical solutions for these equations. But these equations can be solved numerically by supercomputers. This picture shows the ASU agave cluster that we are using to perform geodynamic modeling simulations. In this study, the conservation equations are solved in a 3D regional spherical domain. All boundaries have free slip boundary conditions. The viscosity depends on temperature and depth, and we also include a weak post-perovskite phase transition in the lowermost mantle for some models. We perform both purely thermal and thermochemical models. The Rayleigh number is 10 to the 7 or 5 times 10 to the 7. We use the open source finite element code SiliconCU to solve these conservation equations. Now let me show you the result of the first model. Now you are watching the top of the model. After I make the top surface transparent, you can see the interior of the model. Here the black line shows the model domain. In this model, we initially introduce a layer of intrinsically dense material above the common boundary. Now let's watch how the interior evolves with time. Shortly after the initial condition, the intrinsically dense materials are pushed toward the center of the model domain in the lowermost mantle. Let's pause the video to explain some key components of the video. The green color shows intrinsically dense materials, which form into a pile. Outside the pile, I show the temperature field at 45 km above the common boundary. The arrows show the mantle flow velocity at these depths. The gray isosurfaces show the locations of mantle plumes. We see that most of these mantle plumes form at the edges of the green pile. The cyan color at the north and south boundaries shows the cold dawn whirlings. Let's speed up the video by 3 times. The cold dawn whirlings migrate to the west side boundary, and the green pile is pushed toward the east part of the model domain. The most interesting part is the temperature outside the green pile, near the common boundary. Although these regions are significantly affected by the relatively cold dawn whirlings, there are also lots of relatively hot thermal anomalies in these regions. And these anomalies have a linear shape, extending in the late-low mantle flow directions. This image shows the 3D morphology of the hot anomalies. We find that they become thicker and thicker in the mantle flow directions, and eventually become unstable and form into mantle plumes. For convenience, I will call these linear hot thermal anomalies as thermal ridges. These images show the results of other models. By exploring the parameter space, we conclude that the formation of thermal ridges is not affected by the existence of thermochemical piles, but requires significant CMB heat flux, and is very sensitive to the lowermost mantle viscosity. Generally, low viscosity causes more and smaller thermal ridges. The formation of thermal ridges is also greatly controlled by the thermal structure of the cold dawn whirlings. We find that pre-existing thermal heterogeneities in cold dawn whirlings greatly promote the formation of thermal ridges. So the question is, what causes thermal ridges? We find that the thermal ridges are caused by small-scale convection above the common boundary. For example, let's look into the dynamics of the lowermost mantle. I'm now zooming into the regions outlined by the black box. This is the temperature field in the box at 45 km above the common boundary. Again, there are many thermal ridges extending in the mantle flow directions. Let's now examine the mantle flow velocity in 2 regions. One is before the formation of thermal ridges as marked by the green line B. and the other is after formation of thermal ridges as marked by the green line C. The vertical cross-sections of the temperature field and the vertical component of the mantle flow velocity field in these regions are shown in the right two figures. We find that in Figure B, before the formation of thermal ridges, all the vertical components of the mantle flow velocity goes upward. But in Figure C, after formation of thermal ridges, the vertical component of the mantle flow velocity goes up and down along the profile, demonstrating the development of small-scale convection. Similar style of small-scale convection has also been proposed before beneath the cold lithosphere in the uppermost mantle, and it causes linear shape called thermal instabilities, which are often called the Richter rows. In summary, previous seismic studies have shown widespread low-velocity structures outside the LLSVPs in the lowermost mantle. Like the sublithosphere small-scale convection, hot linear thermal anomalies or thermal ridges also form as a result of small-scale convection from the basal thermal boundary layer. We also find that thermal heterogeneities in subducting slabs greatly promote the formation of thermal ridges. But thermal ridges also form when the slabs are thermally homogeneous. Our results suggest that the regions outside the LLSVPs may contain localized thermal anomalies, which may cause low-velocity structures in these regions. These results also has important implications. First, the thermal ridges may lead to variations of CMB heat flux and CMB topography. Second, they may also cause partial melting in the subduction influence regions above the CMB. The linear shaped thermal ridges elongated in the mantle flow directions may cause or enhance seismic amplitude. Thanks for watching my video. For more information, please check out the following paper or send emails to mimi.li@asu.edu.